So in ethylene, 3 electron regions around the carbon means that they're both sp2, and the sigma bond results from the sp2 to sp2 overlap. And the pi bond forms from what overlap? The p orbitals, the unhybridized p orbitals. Well, they wouldn't be p orbitals if they were hybridized. So it's useful, although redundant, to say unhybridized p. Is it true that you can only have a sigma bond between orbitals of the same type? Let's expand this molecule a little bit more. I'm gonna take ethylene. I'm going to make it not ethylene anymore by adding a CH3 group here. What's the hybridization of that new carbon? How do you know that? 4 electron regions, 3 of them to hydrogens, 1 back to a carbon. What type of bond is here, sigma or pi? Sigma is there, and it results from the overlap of hybridized orbitals. What hybridized orbitals are overlapping here?
sp2 and sp3.
I heard S and sp2, and then I heard sp2 and sp3. S would be a bond with a hydrogen, because hydrogen only has S to offer. But this carbon here has 3 sp2 orbitals to use. 1 to the left, 1 to H, and 1 down here. And this carbon only has sp3 orbitals to use. So any combination of hybridized orbitals can overlap. Now back to this bonding region, which of the lines was the sigma, which of the lines was the pi? That's a silly question, right? Like Lewis structure cannot convey that kind of information. You can memorize that a double bond is 1 sigma 1 pi and a triple bond is 1 sigma 2 pi. You can memorize that because Lewis structures won't convey it. But MO theory will convey it. So I want to take a step back from that complicated MO diagram that we had last week. I want to look at a simpler MO diagram, the one that defines molecular hydrogen, elemental hydrogen. What orbitals does hydrogen have electrons in?
S.
More specifically, Mackenzie? 1s. And how many electrons does hydrogen bring?
1.
Morning. Just 1 electron each. So on both sides, I'm going to draw these as spin up and spin down because I want them to come together to be paired. Now these s orbitals can overlap in phase, and if they do, they get this constructive bonding. They can overlap out of phase, and if they do, they have destructive, did I say constructive bonding? Well, if we say constructive bonding, then we'd have to say destructive anti-bonding. Constructive interference is what I meant, and destructive interference. So what I get down below is what looks like not a sphere, but an elliptical, this big oblong shape. And what I get up above is actually just what looks like 2 orbitals out of phase from each other. The electrons want to move into the lowest energy orbital, so the hydrogen's electrons don't stay in the atomic orbitals, they move to the molecular orbitals where they'll be more stable. Why do atoms bond? The electrons are found in lower energy orbitals. That's why atoms bond. Their electrons are lower energy than they would have been on their own. Lewis structures can't convey that. How do I break this bond? Well, there's 2 ways that I could break this bond. I could put electrons from a different species, like a metal. I could put electrons into the anti-bonding orbital, not sigma because it's occupied, but sigma star. That's our LUMO, our lowest unoccupied, willing to accept electrons, molecular orbital. Or I could take electrons out of the HOMO, the sigma orbital. Those are the two ways that I could break this bond. And if I pumped enough energy in, I could actually take these electrons from the HOMO and I could pump them up into the LUMO, and that would split the molecule apart on its own. Because at that point, it would be more stable for the electrons to be in the atomic orbitals and for the atoms to not be bonded. So molecular orbital theory gives us a really great depiction of why bonding happens, why bonding breaks, and geometry about how that's allowed to happen. If you were to put electrons in here, you would need this phasing to make that happen, which, by the way, looks a lot like a p orbital, the way that it's phased, or, depending on what you're drawing, a d orbital, like from a metal. So molecular orbital theory is great in that, right? But you can't draw a molecule. Like, we can hardly even represent a single bond because we're looking at both the bonding orbitals and the anti-bonding orbitals. So Lewis structure helps us convey structure really well without really understanding bonding. MO theory helps us convey bonding very well, but it doesn't really help us convey structure at all. Okay, these are our two useful pieces. We're going to obviously lean in a lot to Lewis structures because we're going to be drawing a lot of structures. When we get into reactions, we'll come back to MO theory a lot more. Okay, so you've got this worksheet. Saray? Welcome. Right. Imagine a wave in the ocean. Here's your ocean, and now a wave comes through. There's two phases to the wave. There's this phase that rises above your baseline and a phase that rides below the baseline. And if two waves come together and their phases are out of sync, then the low phase of one destroys the high phase of the other, and vice versa. The waves cancel out. But if two waves come together and the high phase meets with the high phase and the low phase meets with the low phase, then they build together and you have an even taller wave. So when we say phases, we're quite literally talking about the behavior of the wave. And the wave in this case is what? Electrons. We're saying that the electron is not a particle. The electron is a wave described by this mathematical equation. Think of this as coming out of the ocean, this as going into the or up and down. Maybe it's a simplification, but it's a useful simplification because of how crazy electrons are. Yeah? So when we say phasing, we're literally talking about, does the energy add together or does the energy subtract from each other? Okay. You guys drew some Lewis structures last week. And it took a little longer than I was expecting, which is like silly of me. I've been doing this for like 4 years straight, teaching OChem 1. I should have known better. Lewis structures can be a challenge, right? You don't draw a lot of Lewis structures in Gen Chem 2, so the last time you really did it was probably, unless you were in Mr. E's lab in Gen Chem 2, you were probably in Gen Chem 1 the last time you drew a Lewis structure. And there's a lot of little details to remember, how many electrons to have, what atom goes in the middle. You're not going to have to worry about a lot of that throughout organic chemistry because there's all of these patterns that will follow. In fact, Lewis structures are terrible for our use in organic chemistry. They're too cluttered. they're too complicated. They have got too much going on that they will make it really challenging to understand the actual chemistry that's going on. So we will introduce two new forms: condensed molecular structure and bond-line structure. Let's start with condensed molecular structure. Condensed molecular structure will assume all of the bonds. Or at least most. It won't explicitly say what the bonds look like. You'll just need to infer by the octet rule and by charges what bonds should be present. For example, I had this molecule up here. Now this molecule already had a little bit of condensed molecular structure because I assumed all of those bonds in the CH3. But I could condense this further, and I could write this as CH2, CH, CH3. To be honest, the CH2 part, that could have also been written as H2CH, CH3. Notice how the subscript stays after the hydrogen, but just whether that group, H2, shows up in front of the carbon or behind it, you have some freedom on how you represent it in a condensed molecular structure. But you are taking the groups of atoms and just writing them out as a list. Now I say that this is mostly, it will assume most of the bonds, and that's because there are some bonds that don't do a great job going in a full line sequence, and so we can draw things coming off of certain groups to make it make a little bit more sense. Maybe we'll show a handful of bonds, but we'll condense everything else. Lone pairs can be assumed here. And I say can because you don't have to, but it is pretty common that you would. But formal charges will never be assumed. Formal charges are always shown. But it takes some deciphering. When you look at this CH2 to CH, as you start trying to draw the structure itself and explicitly show the bonds, you might have to guess at how many bonds are between those carbons at first. You're not explicitly told that there's a double bond, so you're going to have to reason out that they have to be double bonded to get to their octets. The other type of structural communication that we'll use is bond-line structure, sometimes called skeletal structure. This is the one that I'll use the most, so it's the one that I really want you to practice with. There's a number of assumptions, and I'm going to list them. First, assume carbon at every end and bend. If a line points to a specific atom, if there's a bond to a bromine, then that line ends at bromine, and you don't have to assume what's there. But if a line just sticks out into space, then you should assume it's a carbon. So for instance, how many carbons in this bond line structure? Two. I've got one end, a carbon, and one bend, a carbon, and then my other line ends at an oxygen, so there's no carbon there. Two. Assume enough H at every carbon to satisfy octet or charge. Now I say octet or charge because We saw last week on that table that we filled in, charge sometimes means octets are broken. Charge can definitely mean that hydrogens are not present. Now, given that there are no charges shown here, how many hydrogens would be in this structure? 6, 7 with the oxygens. Oh, no, I'm sorry, 6 with oxygens, 5 attached to the carbons. So we want to satisfy the octet at carbon. There must be 3 more bonds on this end, and there must be 2 more bonds in that bend. Look at the bonds that are explicitly shown. Fill in how many more are missing. Okay, and then last one, assume lone pairs. If you want to, but throughout the semester, you have every opportunity to explicitly show lone pairs. I just want you to know that when Bondline is communicated to you, you will not be given lone pairs. You will have to assume them. Okay, 2 more rules. Never assume heteroatoms or their hydrogens. What's a heteroatom? Did we talk about this? Well said. Every other element besides the hydrocarbon template that is organic chemistry. Boron, nitrogen, oxygen, halogens, sulfur, phosphorus, metals. Anything that is not hydrogen and carbon has to be explicitly shown. But more than that, anything that's not carbon needs to have its hydrogens shown bonded to it. Notice in that first bond line that I gave you, I didn't draw the structure like this to allow you to assume that there's a hydrogen on the oxygen. Instead, we explicitly showed the hydrogen that was bonded to the oxygen. Okay, and then the last one is never assume formal charge. Unless I'm designing a question for you to assess you on your ability to determine formal charge, in which case I'm allowed to not show the formal charge, but I'd have to show you all of the hydrogens and all of the lone pairs, because without the hydrogens and lone pairs, you can't determine formal charge. You need one or the other. So we sacrifice formal charge. We always show formal charge so that we can assume all of the hydrogens and all of the lone pairs. Okay. There are a few structures in Bondline that are communicated a little interestingly in condensed molecular form, and I want to give those to you before I have you fill out this table. There is a group called the aromatic ring, and it is a 6-membered ring with 3 alternating double bonds. And it doesn't matter the orientation of those double bonds, just so long as they are alternating. And when we write this as a condensed molecular form, we write this as C6H5. R here I'm using just to represent that it's bonded to something else. There's the rest of the molecule. That could be an OH coming off. And then I would write C6H5OH. There could be a 4-carbon chain, C6H5, CH2, 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 CH3. But when we use the condensed molecular form of this, all 6 of those carbons and the 5 hydrogens that are in the ring get condensed into that one C6H5. We have a lot of CO double bonds that we will get familiar with. So a couple of them look very similar. There's this CO double bond bonded to OH compared to a CO double bond bonded to OR, meaning something else other than H is there. We can abbreviate these one of two ways. We can abbreviate these as COOH or CO2H. So I'm just going to demonstrate those two ways. COO something or CO2 something. You guys okay with that? Both of them are perfectly acceptable. I'm sorry for how light that marker is. I'm going to switch. But there's two other CO double bond groups that show up a bit differently than those two. One is a CO double bond group that shows up at the end of a molecule. So it's bonded to a hydrogen. We'll abbreviate this group as CHO. It's not that there's something wrong with putting COH, but by communicating a group like that as COH, your brain will instinctively think carbon to oxygen to hydrogen. This abbreviation should make you think carbon and hydrogen with oxygen. So by communicating it as CHO, we're able to get a better realistic understanding of what the structure is as opposed to COH. And then if the CO double bond is in the middle of a carbon chain, how do we demonstrate that the oxygen is bonded simply to that one carbon as opposed to being in the middle of the chain? What we'll often do is show this as an O in parentheses. So I'm going to, maybe I haven't been meaning to say that these are CH3s, but that is exactly what I'm saying. So for example, for this case, we could say CH3, CO in parentheses, CH3. But what I want you to pay attention to there is this part in particular. There's a difference there between that and a molecule that has an oxygen in the carbon chain, CH3O, CH3. The parentheses help to remind you that the oxygen is not a part of the chain of atoms. The parentheses is meant to remind you this oxygen belongs only to that carbon. Without the parentheses, your brain will think to put the oxygen into the chain of atoms. Does that make sense?
Would it also be fair to think like there's going to be a double bonded oxygen just every time you see that?
If you've got that parentheses, you should, yeah, I can't think of a reason why you wouldn't think that it's a double bonded O. Exactly. Okay, so these are some of the most common ones that you'll see throughout the semester that are not as easy as just simplify the structure as you wish. I want you to get familiar with some of these. Now, why don't you spend 10 minutes in groups converting those structures on your page between their missing forms? To be honest, you don't have to back convert into the Lewis structures if you don't want to, but it is a good practice in interpreting Bondline as a Lewis structure to something you've seen before. Work together, get in groups. We'll spend about 10 minutes here.
Can I get one of those papers?
Yes. Oh, sorry, Gavin. Yeah, I really hid them from you.
Thank you.
You bet. Yes. Anybody else need one? Did you get one?
Thank you.
You're welcome.
I don't know if I oversimplified that because there's three things of CH2.
I think you have too many carbons,
Maybe.
and because of that, you've got too many bonds going on too.
Is this right, or did I oversimplify it with?
No, that's useful.
Okay.
Yeah, yeah.
Cool.
Both would be right.
Mine too? Is that what you're saying? Or his too?
Oh, no, that one actually doesn't tell me how those atoms are grouped.
Okay.
So telling me that I have 3 sets of CH2
Okay.
is good.
Okay.
The other way would be just saying each of the
Just
CH2s.
CH2.
Yep,
Oh, okay, ready.
yep.
Okay, got it.
Can I get your name?
Rowan.
Rowan.
Yeah.
Welcome to the class.
I was the late transfer.
That's right. Well, you might not be the last one. Glad you made it. Did you get caught up on all the videos?
I've looked at them, probably not as thorough as I want to.
Okay.
Because I joined late for all my classes.
Mm.
So I'm like, I'm in
Big
a
catch
hole
up.
right now.
Yeah, absolutely. Well, you're on track with assignments, it looks like, so that's good.
There's 4 of these CH2s, and then there's one more CH3.
Does that look correct?
Yeah. Yeah, that's exactly it.
Interesting.
You're explaining how it's structured.
Good work. You guys are good with what's on the board, so I can erase this so we can do this activity on the board?
Can you check this one for me?
Mm-hmm. Well, you're going to leave this carbon out here, just bonded to nothing?
Oh, because it's a CH right there.
It is, it is.
Okay. Because you can see like my little pencil marks.
And then, actually, before you go on too far, how many bonds to that guy?
Oh, I should break
Good. That'll help you in solving it.
that. Okay.
Yep.
Thank you.
There was 2 double bonds, or did I draw that incorrectly?
I thought there was only 2 because, only 1 because, then this would be 4, then that would be 4.
Okay.
And Rowan, what you had would have given
It would have had too many of
5 bonds to that carbon.
Okay.
Actually, 5 bonds to both carbons, right?
I guess it's true, right?
So it would just go. Totally.
Okay. This makes sense. So you're telling me these bad boys.
Because the only 2 carbons, it would just be, no, yeah.
No.
One would stay.
Is that how you would write?
You can, absolutely.
That-
Oh, well, we wouldn't actually list these 3 as a sequence.
You do C3H9.
No, because that could have a lot of different ways that it's configured, so that's not a bad idea. We would say CH3, 3.
Oh, that makes sense.
Or we would...
This works, but it condenses more if you do CH3, 3.
I worry this doesn't work because it conveys that these
Are all
come off
bonded
of
to
each other sequentially. To show that one comes off sequentially, the others would need, remember I said we can assume most of those lines, but we can add other ones. I would say the best way would just to say that you've got a CH3 3 times.
Yeah.
Yep,
All bonded to that one carbon.
exactly. Eric, how many bonds you got at this carbon?
Too many.
I see. I agree.
That's what I did in my bottom class.
Great job.
We're blocking you.
No, you're not. You are my way. Chloe, is this your work?
What? Yeah.
You forgot your double bonds in the 6-membered ring.
Oh, okay.
There are 3 alternating double bonds.
They just flip between.
Yeah, without those double bonds, it's very different.
Oh, okay.
For example, if you did have this structure versus having this structure, they're very different molecules, very different reactivities, very different properties. This one would be C6H5OH. This would actually be C6H11.
Oh, because each of those would have hydrogen on the inside. I mean, on the outside.
Correct.
Okay.
And I actually didn't give you this because I won't have you abbreviate that much at all. But this is something that you very well could see, and it's a very common abbreviation.
Thank you.
Yeah, you bet.
I'm tweaking.
Uh-oh.
I can't figure out how to draw this in a loose structure.
Yeah.
All these freaking CHs.
I think you're short of carbon, right? No, you're not short of carbon. You're extra a...
Yeah, I'm short of carbon.
Yeah, you're short of carbon.
Are there a lot of double bonds in this one?
A lot of multiple bonds, for sure. I won't say just double, but multiple, like double and pi. There's a few.
So do we assume a hydrogen is attached to that carbon?
Yes.
So it'd be a CH3
Yes.
CO it'd be CH2O.
Not CH2O, because there aren't 2 H's.
There'd be one. Yeah, 1H.
Yep.
So CHO.
Perfect.
Okay.
Nailed it.
That's an interesting one.
It is.
What did we forget? Number 3.
Yeah.
Oh, yeah, we did.
How about this one, Professor?
Yes. Nailed it. That's exactly it.
Is this right?
That works great.
Is it the most great?
No, remember the 6-membered ring with 3 alternating double bonds? We have an abbreviation for.
That's the.
So it's not that it's carbon bonded to 5 CHs, although that's not a bad way of thinking about it. You should think of this whole ring as one thing.
So C5.
C6
Or-
H5.
Okay.
Yep.
Okay.
Eric, you were raising your hand?
No, sir.
Okay.
That's what I want for Lewis structure because that one has 3, so you need another.
You guys enjoying this? You want to keep going? Okay. I'm enjoying watching it.
Would this be included in this?
Mm-hmm.
Okay.
I agree. You've got that CO double bond with an O and then other stuff. Yep. So either version, you could write it as COO other stuff or CO2 other stuff.
Okay.
The limitation I'm realizing that's not on this worksheet our charged compounds are missing. I didn't put any charges in here, and you will deal with charged compounds throughout the semester. So that's one thing I need to improve on this worksheet. How to interpret between charges.
So you didn't do parentheses here?
No yet.
Could you?
I think it would have been long.
But I see
Generally how they notate that.
You think you finished them all, Andrew?
I think so.
Now down here, I worry that it looks like too many carbons. 1, 2, 3.
Oh, did I put that early? Yeah. Should.
And I think it goes to say that maybe Bondline is not the most effective way to communicate that molecule. Maybe a better way to communicate it is just condensed,
Yeah.
right?
So that'd be correct.
Yes. Now
Yeah.
geometry is off. You've got that bend in it, but it's an sp carbon. Sp carbons have what geometry?
Linear.
Right. So if we were to draw it true to its geometry,
It'd just be 3 straight lines.
yeah, pretty much. But
1 straight line and then 3 straight lines. Yeah.
but to start, that's great.
Okay.
This is perfect. Did you take Gen Chem 2 lab here?
I'm taking it right concurrently.
Oh, you are.
So I took Gen Chem 1 last semester, doing 2 in organic.
Sure.
And then I'll be in your organic 2 next semester.
Good. Your lab this week then is this experiment, I believe. You're going to do a kinetic study
Oh yeah.
making iodoacetone.
Oh cool.
So you're gonna make that molecule. You can tell the rest of your classmates what it looks like. Yes. Mm-hmm. Now without the dots, but I think the dots are you just saying how many hydrogens are there. Yes, that's perfect. Now geometry, we'll talk about the geometry as well, but for its Lewis structure, great. Yep. All right, I would love to have you guys spend the rest of the day on this, but we need to do some other stuff in this unit too. So we're gonna move on. What I will do is give you guys some of the answers. So for our first structure, we're actually just looking at the molecule of hexane, and its condensed form can be written one of 2 ways. You can write out each of those CH2s, or you can group those CH2s as a set of 3 CH2s in sequence. And its bond line form represents what you probably have already seen to some extent, this just traditional zigzag structure. We're actually going to talk next week about why we draw organic molecules as zigzags as opposed to zigzags or zagzags. Zigzag is actually communicating something about the molecule. The next one was pretty challenging, right? This one has a double bond and a triple bond inside of it. Now, what I think most of you did when drawing this one was you started with that zigzag structure, and then you added in the double and the triple bond where they needed to go. Could you tell me what is the difference between those 2 bond lines?
Geometry.
Just geometry. Is that what you're going to say? The geometry is the only thing that's different. The geometry at what carbon? the geometry at the sp hybridized carbon, at the carbon that has only 2 electron regions. Here, those 2 electron regions, a sigma bond, a single bond region, and a triple bond region, are 180 degrees from each other. Here, I just started with that zigzag pattern, and I added in the double and triple bond. So the bond is more like 120, which doesn't agree with its geometry. I'll accept it, but I want you guys to be thinking about how the geometry can be conveyed in these bond line structures. Also, without drawing it, I know it can be hard with those triple bonds to count your carbons. Like here, it doesn't necessarily look like an end or a bend, but I would argue it's the end of a single bond and the end of a triple bond. So it is the end of 2 different bonding regions. Okay, the one in the middle, if we want to draw its bond line structure, would be CH3, CH2O, CH2O, CH3. We could also, it feels a little funny, but we could write this as 2 sets of CH3, CH2 bonded to O. CH3, CH2, 2, O. Our fourth one, the condensed molecular formula, C6H5. There's that 6-membered ring with 3 alternating double bonds. Recognize that the 3 alternating double bonds are significant there. And then we can say CO2, C, CH3, 3. Or we could say COO, C, CH3, 3. Andrew had a good point, which was he had C, CH3, 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 kind of like we did the CH2s up here. But these CH2s are in sequence one after another. And these CH3s are not in sequence. They're actually all connected at the same point. So if you wanted to draw this one differently, you'd have to show those other CH3s with lines. You wouldn't be able to abbreviate their lines. We shouldn't group them and say C3H9, because there's a lot of ways that C3H9 can show up. We'd want to do one of those 2 condensed ways. Rowan?
Different to write like 3CH3, like instead of
Having the subscript after.
yeah, like having it before and like I guess not in subscript.
As a coefficient. So you're saying like this?
Yeah.
It is. Yeah, coefficients aren't part of structure. So we shouldn't use coefficients in there. Thanks for bringing that up. Instead, we should use subscripts as we do with just chemical formulas. That's the idea of the condensed molecular structure. Kind of hybridizes chemical formula with structure. So yeah, I would avoid that at all costs. Now the bond line form, we get to assume all of those hydrogens. And then we get this group on the right, kind of looks like a chicken foot. Much easier to communicate what's going on in that structure with bond line than it is to communicate it with its Lewis dot structure. Its Lewis dot structure is crazy. You're just cluttered with all of this information. It's honestly, in my opinion, hard to see the single versus double bonds in that Lewis dot structure than it is in its bond line form. All right, number 5, we've got acetic acid. So I'm not going to draw its Lewis structure. Its condensed molecular form would be either CH3COOH or CH3CO2H. The next one, we've got an aldehyde. This has 2 CH3s. So once again, we're going to write this as a set of CH3s together with a subscript 2 that are bonded to a CH, a central carbon that just has 1 hydrogen coming off of it. And that carbon is bonded to a CHO group. we could have moved around how we wrote these things. We could have written CH, CH32, CHO. Either one of those would have been perfectly acceptable, because in order for everything to be connected, all of those groups, the H, the CH3s, and the CHO, are all going to have to connect back to this first carbon. Okay, then we've got a condensed form. When we draw this one out, remember it's got that oxygen in the parentheses, so we can start by looking for that CO double bond. On one side, a CH3. On the other side, a CH2 with an iodine. Those of you that did Gen Chem 2 lab here at SLIC, you made this already. When you did the kinetics of acetone, iodine, and hydrochloric acid, you were making iodoacetone. That's the compound that you made in those first few weeks of Gen Chem 2 lab. All right, now the last one is arguably the one that probably is represented best by condensed form rather than molecular form. So our last one, CH3, CN, I don't have to communicate that the C and N have a triple bond. They have to have a triple bond in order to satisfy their structures. But to draw them as a Lewis structure, remember, geometry is important. So I know a lot of you drew it like this because you started with a zigzag. But this can be really dangerous, especially if you are someone that doesn't draw your triple bonds all the way. Do you know what I see here? I see 3 carbons, not 2, with appropriate linear geometry. I see an end, a bend, and then that same triple bond to single bond end. So I see carbon, CH2, C. I see too many carbons in this structure, only because my triple bond didn't reach all the way to my single bond. If my triple bond did reach all the way, now it does look like 2 carbons, CH3 and C. But obeying the geometry in the bond-line structure just really goes the extra mile to convey how many carbons are there. Do you know what happens when we assume things? Do you know why it's dangerous that bond-line structure is built on assumptions? My high school chemistry teacher said, when you assume, it makes an ass out of you and me, which is how you spell assume. And that is exactly what happens when we're doing these structures. I'm assuming that you're assuming the same thing as me, and so we might actually come to different interpretations if we're not assuming the exact same thing.
So we want to draw it linear, is what you're saying?
Because it's an sp carbon, linear geometry is best. I will accept this, especially early on, and especially as we get more familiar with these. I'll accept these and point out what might feel confusing about them, but I really want you to lean into communicating the appropriate geometry. Now, in my opinion, this is harder to interpret and takes a little bit more energy than its condensed molecular form. For all of the other structures, I feel like the bond line form is the best, the most straightforward, gives a lot of information. But for this last one, I actually think condensed molecular form does the best job communicating it. Okay, questions on that?
For question 1, wouldn't it be 4 CH2 because there's 6 carbons, and then that additional carbon would have the 2 hydrogens?
Thank you for calling me out on that, Mackenzie. You're exactly right. I'm looking for 6 carbons. I've got 1, 2. This would only give me 5. So instead of a subscript 3, I need that subscript 4. I'm going to put that in a different color so it stands out. Thank you.
Also have another question.
Tell me.
For like any like COOs, can we put like a additional parentheses around one of the O's to say that's a double bonded oxygen?
Yeah, you know what? You could put one of those O's in parentheses. just like how we did with the CO double bonds in the middle. I think in theory you could also do it here, although the idea that we write it as CHO leaves no space for it to show up any other way than to be double bonded. I like this idea of indicating one of them is double bonded, one of them is actually a part of the chain. Great. Anything else? All right, well, now I remember, I did give you a chance to deal with formal charges and Lewis structures. So I want you guys to go through, especially with that table that you made last week, with all of your different bonding patterns and the charges and the lone pairs. I want you to fill in on this first set, these first 3 molecules. Pay attention to the heteroatoms. The carbons are all satisfied. Pay attention to the chlorine and the oxygen. Based on the lone pairs that are present, I want you to fill in the charges. By the way, these are molecules, these are structures that you will be drawing later in the semester. So I'm giving them to you now as a preemptive practice on recognizing what they should look like. So draw in the charges. On the 4 structures on the right, add in the lone pairs based on the charges. Once again, unless the carbons say it, the carbons are satisfied. So formal charges, lone pairs. Why don't you take about 7 minutes to go through in your groups, add in those missing charges, add in those missing lone pairs. And leverage that table from last week if you can. I don't have any more of them. Sorry. It is on Canvas, though. And if you send me a reminder, I can try to bring one tomorrow. Yes.
Where could I find this?
Scroll down to Unit 1. Yep. And then that charges, bonding, and hybridization was the first document we did.
Okay.
And Bondlines and Polarity is the one we're doing today.
Thank you.
You're welcome. You guys are good with all the structures I drew over here. I can erase that. If anybody needs a picture, now's a great time. Yes, it is.
Okay.
Yes, the bromine is bonded to both of them.
That is weird.
Yes, it is. And you're going to draw that later in the semester. I tell you what, I do my best not to draw anything or not to give you things early on that you're not going to need to be familiar with throughout the OChem sequence. Is this going to give you a positive? Think about that.
No, it'd have 0.
There you go. There you go.
Are we just looking for the charge of the hetero atom?
Yes,
Okay, so that would be correct, right?
correct.
Okay,
Great work.
I just forgot the formula.
So I didn't give this filled out, but top row is positive charges, middle row is neutral charges, and the last row is negative charges. So it'll be +0 neutral. And one of the goals of this in-class activity was to add the lone pairs as necessary. I actually didn't change the wording that I should have. I should have changed the wording up here. But it was show the charges and show the lone pairs.
Okay.
So, for instance, like there was one lone pair on each oxygen here and a positive charge on each oxygen. Have you found the lecture recordings
Yes.
from last week? Did you watch through them?
I watched a few.
Okay. I think when we did this one, my microphone was dead. So it would have just been a video of copying things down from the board and not hearing anything. Good work. Yep. I mean, if yours looks like hers,
Yes, it
it's
does.
right.
Perfect. How'd you know?
Okay. Great start. So Rowan, are you saying that this oxygen, despite the change that it undergoes, keeps a charge?
No, it doesn't, does it?
Sorry, Saray.
With 3 bonds and a lone pair, it's +1. But
Yes,
then
right.
with 2, it's just stable.
Yeah, now think about this organic piece being gone
Okay.
and that bond going to a hydrogen. You know what molecule that is?
H2O.
Right.
Yeah.
Which is neutral.
Yeah.
So think about the patterns you already know feed really well into this class.
Okay.
Good. So it's got an octet and no radical unpaired electrons. Good.
What are you talking about when you mention like Lewis structures in Mr. E's lab?
Oh, so he he really loves his polyatomic ions. He wants to know that students know the name and the charge. I guess I assumed that he had you draw them too, but maybe just name and charge, name and formula.
I think he just made us do name and charge,
Right,
and I guess formula too.
but not structure. That would have been the only time you would have drawn a Lewis structure otherwise, is if you drew out those polyatomic ions. So yeah, maybe I was wrong on that.
I don't know if he made other classes do it.
No,
It doesn't always seem the most organized.
but you
Kindest way.
but you had him just this spring. Yeah, that's what I was thinking of even. So my guess is no, I was wrong on that. Thank you.
I think it's not a big thing.
But it is funny, right? Like we teach you how to visualize these molecules and their structures in Gen Chem 1, and then it's like, poof, never matters in Gen Chem 2. And then you come back to OChem 1 after taking all that time off, and it's like very important again. You know, I think a better sequence, like if we could just like wake up the educational system of the world, I think a better sequence would be Gen Chem 1, OChem 1, Gen Chem 2, OChem 2. Gen Chem 2 is very reaction heavy, but it's the math behind reactions. OChem 2 is very reaction heavy. There's not a lot of math, but some of the things we learn about the math of reactions is useful in there. We just don't touch on it. But I think that's because we don't touch on it because it's so far back, you know? Like it doesn't, you've already covered it, it doesn't really apply. But if you'd covered it the semester before, we could make so much more sense of it all. Gen Chem 1, OChem 1, Gen Chem 2, OChem 2. You don't have to do anything, but you could if you wanted to. I've had students take OChem 2 just for fun, and then they find that it's useful for their degree.
I'm going Chem E, so I gotta take everything.
+1, +1.
Neutral?
Oh, okay. I didn't read that right. I thought it was a +1. Good.
Okay, awesome. 1, 2.
All right, so I think most of you have gotten through that first part. So I'm going to add these charges. Formal charge is valence electrons minus lines plus dots, dots plus lines. So I've got 7 valence electrons on my halogen. I've got 4 dots and 2 lines, so that's 7 minus 6. What we're communicating is that chlorine is sharing more electrons than it would prefer. True or false? This means that chlorine does not have an octet. It has an octet despite despite having a formal charge. Those two things are completely separate ideas, right? It has an octet and it has a formal charge because it's sharing more than it would like to. Now in the next step, the oxygen has bonded, and the oxygen has 3 bonds. 3 bonds and 1 lone pair on oxygen. That's a neutral bonding pattern for nitrogen, which means for oxygen, it's sharing more than it would like to. So oxygen takes on the positive charge. And then in the next step, no charges on either heteroatom. Now going back in, I want you guys to think about how you've already seen some of these. Okay, carbon with a positive charge, 4 minus what gives +1? 4 minus 3. And I've already got explicitly shown 3 bonds to carbon. So am I adding lone pairs here? No, I'm not. Oxygen with a negative charge. Well, that means that it has more electrons than it would prefer. It's sharing less than it would prefer. It prefers to share 2 bonds. I see 1, so less than 2 is 1. The rest of the electron density must come from lone pairs. 6 minus 6 plus 1, -1. All right, is bromine going to be any different than chlorine when it's bonded twice? Bromine should look exactly the same. So a positively charged bromine with 2 bonds is just like a positively charged chlorine. There are 2 lone pairs on that bromine. Guys, I'm giving you structures that you're going to see all semester long to get you familiar with them early on. So don't think that these are just random molecules. You're going to draw these molecules later in the semester in reactions. How many lone pairs here? Yeah, think back to where you saw oxygen with 3 bonds and a positive charge last. It still had 1 lone pair. I want that to feel super easy, going back and forth between charges and lone pairs. Because on your exams, I'm happy to put questions that have lone pairs and have you tell me charges, or that have charges and have you tell me lone pairs. So be comfortable going between them.
I just want to clarify for bromine. So because we have 7 valence electrons subtracted from 2 bonds, it gives us +5. So we want to add 4 electrons to get +1. The lowest formal charge possible.
That's a great way of doing it. We know that it has 7 valence electrons. We can see that it has 2 bonds. That leaves us as +5. But I need to get to +1. So I would need to have 4 dots. That's right, yeah. We're almost always going for an octet here. All right. Now, in the context of bonding, we are almost always going to be drawing covalent bonds and covalent molecules. Obviously, ionic bonds don't have a line drawn between them. Ionic bonds we would draw as separate cation and anions. But when it comes to covalently shared electrons, they're not always shared equally. So I've given you this big long molecule, and I want you to go through the highlighted bonds, the ones that are bolded. And I want you to place partial charge. I want you to determine where the bond has more electron density and where it has lost electron density. Now, there are two things that impact a dipole. There's the difference in electronegativity. That delta, that triangle, means change or difference. If the difference in electronegativity is less than 0.5, 0.4, 0.5, we consider the bond to be nonpolar covalent. Covalent, you guys hear that, is like co-parent, co-pilot, covalent, sharing valence electrons. We would say that it's nonpolar, which does not mean that it doesn't have partial charges. It just means that we don't consider its partial charges. If the difference is between 0.5 and 1.9, we consider the bond to be polar. And if the difference in electronegativity is greater than 1.9, the bond is considered ionic. So with polar, we can draw an arrow. This is a dipole arrow. The dipole arrow points toward the more electronegative atom and away from the less electronegative atom. But I personally don't like drawing dipole arrows. I'd rather draw partial charges. And the partial charge is this Greek letter delta, which kind of looks like a fun little S. Delta negative, delta positive, partial negative, partial positive. However, bond polarity is not just determined by difference in electronegativity. It's also determined by the size of the bond. For example, carbon to iodine has a difference in electronegativity of, do you guys want to take a guess? Give me a number or where in the range it falls.
It's like polar, like between 0.5 and 1.9.
Polar, so maybe around 1, 0.8. So your gut tells you, what you're listening to right now in your body is called chemical intuition. You've been familiar with some of these bonds. You know how to apply things without necessarily having a reason. It's intuitive to you that it's a polar bond. So the difference in electronegativity must be greater than 0.5. Electronegativity is not something we need to have values for a lot in this class, but you guys know that it increases to the right and up. So compared to fluorine, which is the most electronegative atom on the table, iodine is less electronegative. It's all the way at the bottom of the halogens. Didn't see that coming, did you? Carbon and iodine have the same electronegativity. But this is not a nonpolar bond because it is such a long bond. It's a long bond, which means the electrons are dispersed over this huge area. And when you think about the size of that area, carbon's atom makes up this much, and iodine's atom makes up this much, right? Iodine is a much larger atom than carbon. So where do we find the electrons most often? Around iodine. So iodine is more negative, not because of a difference in electronegativity, but because of its bond size. Partial positive, partial negative. Electronegativity plays one factor, bond size plays another factor. So I had a Gen Chem student this last spring that messaged me and said, do I need to memorize all these electronegativity values to be able to predict which bonds are polar and which ones are not? And the answer was, after quickly looking, no, you really don't need to memorize. In fact, it's easier to memorize which bonds are nonpolar. Almost all of the elements, all of the non-metal elements bonded to each other make polar bonds. There's very few elements, especially bonding to carbon, there's very few elements that make a non-polar bond. For example, the difference between C and H has an electronegativity difference of 0.4, which I believe is why the cutoff is 0.5, because somebody wanted carbon to hydrogen to be called nonpolar. So they drew a line in the sand at 0.5 and said, carbon to hydrogen is nonpolar. Gavin, I passed over your question.
Is that, for instance, for iodine, is that related to, what is it, electron affinity or like atomic radius?
It's more about atomic radius because iodine is in such a large energy shell.
Okay.
Remember, the size of the atom comes from what? The nucleus or the electron cloud? The electron cloud. So iodine's electron cloud is huge. Actually, relatively speaking, their nuclei are pretty much the same size. Despite having a lot more stuff in the nucleus, their nuclei are much, much closer in scale than their electron clouds are. So it's not about their electronegativity, which is more like electron affinity.
Okay.
It's more about their atomic radius.
So if our radius is larger and we have a similar electronegativity, we can always assume the larger radius will have preferential treatment for electrons.
Larger radius, partial negative. That's exactly right. Okay, so is it true that carbon to hydrogen doesn't have a dipole moment, that its bond is not more positive or more negative in one region than the other? That is just categorically not true. One atom is more electronegative. So when you look at this bond and we call it nonpolar, you can still put partial charges. Where would the partial positive go? The hydrogen. And the partial negative to the carbon. It's a nonpolar bond. And this is how the charge is distributed. Isn't that just the silliest thing you've ever heard? I hate it. I hate it here. I hate this. I hate whoever did this. The CH bond has a dipole as a non-polar bond. Are you okay with that?
Sure.
Yeah. I feel like you just have to accept it. I have test questions that say, which of the following bonds is considered non-polar? Is this a trick question? No, because I'm teaching you out of the standard of chemical education that says CH is a non-polar bond. Everyone in the world will agree. But if I ask you to place charges, you should also be able to do that because you're just following electronegativity. You okay with that? Okay. So why don't you go through and fill out partial charge distribution across all of those bonds. I'm going to draw this giant molecule on the board, and I'll have you guys tell me where the charges should go. But take about 5 minutes or less to fill these in.
I printed all this stuff off in Chem 1, like funny stuff. I have like electron affinity values, atomic radius, like all the freaking
Nice.
My question with the nitrogens,
Rank. I don't know why I said rank. Classify.
is if it lands on 0.5, do you consider it polar or non-polar?
Yeah, this is a line in the sand.
Okay.
So it's really hard to say. You don't have to agree, but I'm telling you that this is a spectrum. That's the definition of a spectrum, ranges from one end to the other. And we have drawn lines in the sand to create boxes. Why did we draw the lines where we did? That's really not how spectrums work. If we were to say this better, we'd say this is more nonpolar, more polar, until there's a region where the polar and ionic bleeds together, and then we have true ionic. So if a bond difference landed at 0.5, hell, I'd tell you that the CH bond is polar. So if it landed at 0.5, I'd say polar. If it lands at 0.2, I'd say polar. The difference between the B and H bond is 0.1. And later in the semester, your textbook will say that that difference in electronegativity drives the way a reaction occurs. Really? A difference of 0.1 is meaningful to the reaction, but a difference of 0.4 is just like throw a whole class of molecules out the window? Evil. Evil. Okay.
So the only true covalent bonds would be like O2, something like that.
Was CH. OO. HH, exactly. Pure, or otherwise called pure bonds. Yep.
Pretty safe to say in this class that like oxygen is always mostly going to be the or like partial negative.
Oxygen is the second most electronegative atom,
So unless it's fluorine.
and it's not even close. Oxygen, the next closest one I think is chlorine, and it's 0.5 above chlorine.
Okay.
Yeah, you're exactly right. The only reason O would not be partial negative is if it's bonded to F, which it almost never is, or if it's bonded to itself.
Oh, yeah. And then you have to look at what else is on it.
Yes. So remember, you're just looking at the highlighted bond pairs.
When they're bonded together,
Mm-hmm.
does the hydrogen affect that?
Now you could look at the N to H bond and talk about partial charges across N to H. But if you're looking at the N to N bond, why would there be a difference in electronegativity? Why would there be a partial charge? They would share those electrons very equally.
Okay.
Right? Think about molecular nitrogen, N triple bond N, no partial charges. Same thing with molecular oxygen. What are you thinking? N to O?
Yes.
So you're trying to say whether it's polar or nonpolar?
Right.
If it's not C to H, it's polar.
Polar. Okay, so that's,
Isn't that crazy?
if it's not C to H, it's
Any combination of your nonmetals is almost always a polar combination.
okay.
It's definitely in OChem, maybe not in like inorganic chemistry.
Yeah.
Like sulfur to chlorine might be considered nonpolar. Sulfur to bromine might be considered nonpolar.
Okay.
But the bond size then really changes too. Sulfur to bromine is a big bond, so it probably still is polar.
Okay. That's very helpful.
So really, just get in the habit of thinking, where does the partial charge go? Now, what are you thinking here? Carbon to carbon double bond.
Yeah,
What's the difference in electronegativity?
basically zero.
Yeah.
But because you said this is polar technically, would that give, having the two hydrogens would give this carbon a bit more electronegativity than normal?
Well, no, because electronegativity is true of the nucleus more so than the atom itself.
So these would all be non-polar.
I agree. Now, you're off to a good start which in thinking that what is around it might be impacting the real nature of the bond, but I do want you to think of these, at least for now, as being
Non-polar.
nonpolar bonds.
Sorry, I wasn't paying attention. So, am I determining between like these two?
That's right.
Okay,
Yeah, for each of the
heteroatom?
highlighted bonds.
Okay. Oh, the highlighted bonds. I thought that was three-dimensional. Oh, okay. Gotcha. Thank you.
You're welcome. All right. Oh man, we're so close, huh? Okay, so I want to go through these with you guys, and we'll just do a brief intro into polarity as a molecule. In order to think about polarity of molecules, though, we have to have the polarity of bonds down first. So without needing a table of electronegativities, you were able to solve this based on the principle that most nonmetals bonded to each other have polar bonds. The only exception is the C to H. But if you have a nonmetal bonded to itself, then you also have a nonpolar bond. So the only ones in here that I don't expect you to put partial charges on are these bonds to themselves. O to O, no charge. N to N, no charge. Andrew had a good point, and some of you were also thinking this. What about this CH2, where this carbon is stealing electron density from the hydrogens, but the carbon on the bottom has nothing to steal it from? So despite the fact that there is no difference in electronegativity, maybe there is a partial negative and a partial positive. We'll come back to that later in the semester, and we'll talk about partial charges on carbon-carbon double bonds. But for now, I'm okay with you thinking about these bonds between these atoms as being no charge difference. These are your only nonpolar ones. Now, where I have a bond to H, H will be the partial positive. So here, O to H, partial negative on O, partial positive on H. N to H, those are my only ones. And then where I have a bond to carbon and a heteroatom, partial positive goes on the carbon every time. C to O single bond, partial positive on the carbon. How does that change if I have a C to O double bond? Does the difference in electronegativity change based on the number of bonds? No. So a double bond, partial positive on carbon, partial negative on O. The same thing for my nitrogens, partial positive on carbon, partial negative on N. The same thing for my halogens, partial positive on carbons, partial negatives on the halogens. What about N to O? Mackenzie, could you grab that door, please? Or thank you, Rowan. Right, electronegativity trends to the right. O is to the right of N. So partial negative on O, partial positive on N. Great. Okay, and sorry, I forgot to fill in all of these, but same exact principle. Now that's looking at how charge is distributed unevenly, asymmetrically in a molecule, and in a bond, excuse me. And saying that this part of the bond is more negative, this part of the bond is more positive. But how does that translate to the molecule at large? When we talk about bond polarity, we are not talking about molecular polarity. So I want to talk about molecular polarity just briefly. There's a rectangles and square relationship between polar molecules and polar bonds. You guys know the rectangle and square relationship? All squares are rectangles, but not all rectangles are squares. All polar molecules have polar bonds, but not all molecules with polar bonds are polar molecules. So a molecule must have a polar bond. It must also lack some symmetry. That lack of symmetry can show up in a number of different ways. A lack of symmetry might be central atom has lone pairs. So it has a polar bond to something, and it has a lone pair, its non-bonding electron pair. Those two groups are never going to be symmetric to each other because bonding to something is not the same as not bonding to something. There's a lack of symmetry. And by that lack of symmetry, the molecule at large will have a dipole. There will be a region of the molecule that's more negative or more positive. or the central atom has different types of bonds. Meaning it's got a dipole from this bond to a chlorine, but it has no dipole from this bond to hydrogen, and so the dipole for chlorine impacts the entire molecule. So that Venn diagram that I was talking about before, rectangles and squares and such, here is methane, no polar bonds, non-polar molecule. Here is tetrachloromethane, polar bonds, non-polar molecule. Shoot, I put that in the wrong spot. Sorry. CCl4, polar bonds, non-polar molecule. And then we have chloroform, or actually I think I'll do dichloromethane, CH2Cl2, has polar bonds and is a polar molecule. Non-polar bonds, non-polar. Polar and non-polar bonds. Polar molecule. And in the middle, I have just polar bonds, non-polar molecule. Okay, what we'll do when we start our class tomorrow, and I'll have a new worksheet for us to go through as well, we'll talk about whether these molecules should be thought of as polar, non-polar, or whether the molecule as a whole should be thought of as an ionic compound. So we'll be revisiting kind of that first activity that we did last week, Wednesday. All right? Have a good day. I'll see some of you guys in lab this afternoon. Otherwise, I'll see you tomorrow morning.